the essence of effective field theory, and there I have mentioned about the three big pillars of the effective field theory, which is basically the bottom-up approach, the top-down, and unfolding, right? And as I mentioned, that bottom-up approach would be more symmetry-driven way of understanding. The top-down would be more like field theory way of understanding this thing, because we will be dealing with different kind of theories, and we'll try to see whether we can have some kind of a universal structure of this top-down effective field theory first. And then unfolding is more guided by the symmetry, partly quantum field theory, and also more importantly driven by the experimental data. So these are all three complementary approaches. So we start with actually the bottom-up approach, because that is what I think is the most important aspect of the effective field theory. Okay. Now, before jumping into the effective field theory, let's try to understand what we are going to construct, okay, and what it is. So this is important when you do not have any kind of clue about our high energy theory or the UV complete theory. So what we have, the energy range which is accessible or explored by the experiments. So we have the knowledge about the symmetry and the quantum fields. So if you have these two information, based on that, close the door properly. Based on that, we try to construct basically the collection of operators. Okay. So now, before really highlighting the effective field theory, let's try to understand how to write down the Lagrangian, because all of us are familiar with quantum field theory. So for a given theory, we know how to write a Lagrangian, whether it's a scalar field or the fermion field, and we know there is some kind of symmetry and so on, so we write down the Lagrangian. But while writing the Lagrangian, what is the most important aspect? I mean, possibly we do not think about that way. That's what we need to learn first. First of all, we want to construct a Lagrangian which is gauge invariant, because at the end of the day, we will try to work with a theory which is gauge invariant. Otherwise, there are a lot of incompleteness and inconsistencies will be faced later on. So we don't want that thing. So we want to construct a Lagrangian which is certainly gauge invariant. Now, to do so, what are the possible ingredients we take for generic theory? So you have a scalar field phi, you have a fermion, okay, and then how to incorporate the gauge theory. So gauge theory are basically that information is embedded in three pieces of information. What are them? One is basically the field tensor, which you write down as the F mu nu, the gauge field, and what is the third one? Covariant derivative. What you call it, d mu. Right. Now you see, to construct the Lagrangian in a gauge invariant way, we do not include the gauge field as our degree of freedom. The gauge field are actually masked within the field tensor and also the covariant derivative. Right. So if you want to write down, you can write down, but you have to be very careful, and that is most of the time you will make a mistake and you will end up with writing a Lagrangian which is possibly not gauge invariant. So that's why this is not a good degree of freedom for us to construct a gauge invariant Lagrangian. Okay. And all these statements, what I am making about the Lagrangian, I'll extend these ideas when we talk about the construction of the operators beyond dimension 4. Because when you write down an effective Lagrangian, okay, that is very similar what you have written down already up to dimension 4. Only thing will extend them beyond dimension 4. Okay. So these are my degree of freedom to construct the Lagrangian. Yes. Yeah, we'll come to that, because it is not guaranteed that whenever the d mu is present, it equivalently replaced by the f mu. So they are independent degree of freedom. Okay, they are independent degree of freedom. D mu is not F mu. You construct F mu for a particular antisymmetric combination of that. But you don't have, for example, when you write down the scalar kinetic term, do you write down in terms of F mu there? You cannot, because that's a symmetric component, right? So that's why there. So F mu is a particular antisymmetric combination of the D mu. It's not the whole information about the D mu. Okay, yeah. Up to this part, any question? Fine. So now, once we identify them, what is the next task we do? The next task basically, we identify what are my symmetries. Now broadly, we classify this symmetry into two parts. One is space-time and one is internal symmetries. And these internal symmetries again classified into two parts. One is basically global and some of them are gauge. So these are symmetry informations. So now the internal symmetry, we have learned different kind of symmetry. You have already, if you have done course in particle physics, you know in the standard model you have a SU2 cross SU3 color cross E1 hypercharge. These are the all internal symmetries. And what are the global symmetries you have there? Baryon number like E1b, E1l, those are the global symmetries. But one thing is common among them, that we will work with the internal symmetry which are basically compact and connected. So we will work with those internal symmetries which are compact and connected. Why? Because the kind of field theory and we will want to construct which are basically relevant for the experimentalist point of view, and there we work with the scattering in all those processes which is basically unitary and finite dimension. Yes.
So we have gauge groups. So we cannot expect any polynomials of A.
In which connection is your question, about symmetry or the degree of freedom? Yeah.
Then we cannot expect gauge field polynomials.
Do you really expect that?
I don't think we do.
Exactly. That's why gauge field doesn't come.
That's why it is not important to
Exactly.
consider
That's why mu, if you try to write down in terms of mu, you will be in really trouble.
Yeah,
Because
so
you will end up with writing such kind of polynomials which are not gauge linear. For example, mu. Okay,
but
which
if
is
you
not
just
gauge
look
linear.
at space-time, then mu is fine.
Space-time I haven't commented out, so I will not go there now. Yeah. So now we will work with unitary and finite dimension representations, and as you know, this compact group have this unitary representations which are basically finite dimension, right? So we will restrict our internal symmetry to that. But what about the space-time symmetry? Space-time symmetry, I don't have a handle and to choose that thing. It's there, right? And we'll restrict ourselves to working with 3+1 dimension. Most of the construction is independent about this choice of 3+1 dimension, but at certain point that will be important. And let me tell you that exactly the where we will choose 3+1 dimension and why it is important about the 3+1 dimension. That the space-time symmetry, for example, if you talk about the SL2C or SO3,1, okay, they are non-compact. Now for the non-compact, the representations are not unitary and finite dimensional both. They do not satisfy simultaneously. Okay. Now the problem is with that, the construction that we will go with, if they do not follow this, we have to reduce and we have to realize those non-compact groups in terms of their compact groups. And for 3+1 dimension, we can do that by going to the wild representations where we write down SU2L and SU2R. I mean the chiral representation. So all non-zero spin state will be projected into two left and right chiral state, including, it's not about the fermion, but also the spin 1 state. For example, field tensor, right? The field tensor will also be projected into two components, which is basically, let's say, F mu L and F mu R, the right component. Okay, and then in the wild representations, we first construct them because this SU2L cross SU2R, these SU2s are basically compact. So they have a unitary and finite dimension representations. So I can really construct those, invariants and information. Then what I can do actually, there's a way to go back from the wild representation to the 3 plus 1 dimensional representations, and by using some kind of relations. For example, for the psi, you can write down as a direct sum of psi l and psi r. For f mu nu and f mu nu tilde, you can write down in terms of you are familiar with f mu nu tilde, right? It's a dual tensor. The tensor and its dual tensor can be written as a complex linear combination of f mu nu l and f mu nu r. So if I can write down everything in terms of f mu nu l and f mu nu r, I can go back and write down in terms of ff dual, and that's how I reconstruct my whole Lagrangian. But the game that I played here for the going from non-compact representation to in terms of some compact representations, that I can do only for 3 plus 1 dimension. That's not a very generic true for any arbitrary d plus 1 dimension that is not yet known. Okay. So that's how I will deal with the symmetries. Okay. But now the question is basically, if you try to recall, when you again write down the standard model Lagrangian or any kind of standard Lagrangian, what we look for? We look for the club of those different kind of degrees of freedom, and you try to make a singlet under the symmetries, right? And you have to keep in mind that all the terms have to be singlet under each and individual symmetry. For example, you write down a term which is singlet under internal symmetry but not singlet under space-time. It's not allowed. It has to be simultaneously satisfying the invariance under each and every symmetry that you have incorporated. Otherwise, those terms will be breaking those kind of symmetries. Now, when we do this thing manually, okay, we can write down all possible terms, okay? But what we can most of the time end up writing either same terms repeatedly in a different form, okay? Or sometimes we write down we miss out some relevant terms, because if you do just by looking into them, and up to dimension 4, the mistakes are less, but it could be if you are working with multiple higher dimension representations. Why? What is the meaning of a higher dimensional representations? All of you are familiar with the Young diagram? How do you construct a higher dimension representation from the lowest dimensional fundamental representations? By taking a tensor product. So, long story, you can think of like the higher dimensional representations contain multiple tensor indices. And if it contains multiple tensor indices, what does it mean? That means basically the possible way of contracting those indices are many more. For example, if you have a SE2 doublet scalar, right? For example, standard model Higgs, you can write down only one term at the quartic level or dimension 2 level, h dagger h whole square. But if you replace h by a complex triplet, it's not only one term, you can write in 3 different terms in the quartic level. Because it's a triplet, so it has more tensor indices compared to the doublet, because doublet is just a vector, you have only one index, okay? But triplet has 2 indices, so you have a more way to contract them, right? And that's why when you deal with multiple higher dimensional representations, if you try to do manually, you will end up writing some wrong terms and this thing. Now, we have to write down the operators which are independent and form a basis. And when I'm saying basis, it's in the same spirit when you talk about the basis of in the vector space. That means, like as you know, in the vector space, if you have a n dimension, if I write down any n plus 1th vector, I should be able to write it down in terms of the other vectors. That means it's not independent. Now, in this particular case, for each and every mass dimension, I should be able to write down a collection of operators, okay? And those operators must be independent from each other. Now, the question we can ask, when I'm saying independent, independent by what kind of virtues? It's not about the same spirit at the orthogonality and all those, of course, but the definition of orthogonality or independence is a different thing here. If you try to recall, when you write down the Lagrangian, we write down the Lagrangian in more fundamentally when you write down the action. For example, okay, let me write down ddx, right? So that is how you plug in the Lagrangian density in the space-time measure and write down the action. So because of this structure, you have always a provision to perform the integration by parts with respect to the space-time indices. So now, coming back to this guy, d mu sitting here. Now, if let's say you have some kind of operators, okay, which contain d mu. So when you plug it here, then always you can do an IBP or integration by parts with respect to that d mu, and you can write that same operator in a different form. So a priori, if you do not have a proper knowledge how to construct a systematic, mathematically rigorous way of constructing the operators, you may end up writing two different structures because both are invariant under the symmetry, but they are related to each other by integration by parts. So if two operators are related to each other by the integration by parts, we will not call them independent. Okay. And there's another aspect is important, which is the equation of motion. For example, if I'm talking about, let's say, constructing dimension 6 operator, okay, and okay, by the way, when I'm talking about the dimension 6, is automatically it's not the space-time dimension, mass dimension of the operator. Okay, so when I'm talking about the mass dimension 6 operator, then two operators may be related to each other by the equation of motion of either phi or psi or the field tensor, because they are the dynamical variables. They are not the like a background field. They are dynamical variables, right? So they have an equation of motion. So when you write down the Lagrangian, you first write down the Lagrangian up to dimension 4, okay, and then you construct the Euler-Lagrangian equation of, yes, come, close the door, equation of motion up to this dimension 4, and then you basically plug those equation of motion in while constructing the operator of dimension 6. Then what you will find out that some of the operators related to each other by the equation of motion of these fields. So again, if two operators relate to each other by the equation of motion, I will not call them independent, they are actually dependent. So now you can see the first task. So basically when you write down the final form of the Lagrangian, which is basically collection of operators, the three steps are important. One, identify your symmetries and the degree of freedom. Second, okay, so when I'm saying identifying, automatically you know how this field transform under the symmetries. That information is already encoded. Second is basically write down all possible invariant terms. Third point is basically check which structures are related to each other by the IBP and equation of motion and remove them. So and then you will end up writing only those operators which are independent. Okay, and that's what is our goal when you construct the operators in the not only the effective field theory but also when you write down the Lagrangian. Okay, yeah. Any question up to this part?
So when you perform that, we may get a total derivative of terms. So
yes.
Do we drop that total derivative terms?
Yes, that's a good point. Because at this point I am talking about the space-time manifold, which is basically non-compact because there is no boundary here. So I'll always remove the total derivative term, because Lagrangian you can always add the total derivative term if the manifold is non-compact. But certainly that's an important thing to think about, and we'll see when you talk about the finite temperature. When in the context of finite temperature, one of the manifold, one of the direction is compact. For example, circle, there's a boundary. So you have to be careful along non-compact direction only you can impose those total derivative term, but not certainly this thing. They will give you boundary operators and all those things, some topological structures and coming. Yes, yes. Yeah.
So in those theories, the two operators related by this integration by parts may not be independent.
Exactly. They will be counted as two independent operators.
So if I'm doing EFT on a sphere.
Exactly. Yeah. And one of the simplest example that I can tell you, for example, all of you are familiar with the scalar kinetic term, right? And you can see that you can write down d mu phi, right? This is the scalar kinetic term. And someone says, no, I don't like this one. I like to work with this structure. Right? And both are invariant under the symmetry and all those things, space-time, whatever you impose. But these are not independent because of the IBP. Okay? So what you can do, you can see always, you can write down this kind of term, phi dagger d mu phi with the total derivative term, right? And if you split that, you get these two operators. So because this is, you are throwing means basically you are setting that to be 0. That means these two are equivalent. But again, if you say, no, I am writing this kind of operator on a sphere where the boundary are there, then these two are independent operators. They are not dependent. Okay? Yeah. Any other question up to this part? Yeah, yeah.
very silly question. You
Yeah.
are dropping this term like capital D.
Yeah.
You have del mu plus a mu, right? So
Sorry, which one?
This total derivative thing that you are dropping.
Ah.
For example, if you want,
No. So basically, when you talk about in a gauge invariant way, your d mu is treated as a total derivative. So there is no hidden structures there.
oh, so you are saying if you don't drop that term, then you lose
Yeah.
the gauge invariance. Okay.
Okay, so that means basically that's a very, it's not a silly question because that's the first question people ask every time when we start this thing. It's good that you have pointed out. So basically you have to register in your mind and you replace all the del mu by the d mu and all the property of the del mu satisfied by the d mu. That's all.
Nice.
Because at this point in this cost you are blind to the inner structure of the d mu. So you treat it as like a derivative. And that's how, if you remember, when you talk about the covariant equation of motion, we don't use the del mu, we use the d mu because property is the same thing. Right? Yeah. Any other question? Yeah. That's why please ask the questions because sometimes I may, slip some of the points, but it will always help me to get back to those things. Okay. But this is all blabbering we have done so far. Now we'll do the mathematical way of how to deal with that thing. And that's where the Hilbert series approach comes into the picture. Okay. Fine. So I'll talk about before. So this is the natural unit, right? And everything basically are related. So I have a scalar field mass dimension 1, F mu mass dimension 2. So I'm working 3 plus 1 dimension again. Is 3 by 2 and d mu as 1. Okay. So this is the counting of this thing. And before I proceed, let me make another important point about the d mu, that d mu is a covariant derivative. Okay. And these are the property of the fields are here. These are the dynamical objects. This drives the dynamics, but this is not itself a dynamical object. Okay. And what does it do? It actually sit in the operator, and we have to give this d mu as the same status of a quantum field, but not as a property of the quantum field, but more like a spurion. So spurion, when you introduce, basically their presence are on the on shell. Why? Because as you can see, there are operators which involve the momentum, right? Like derivative scalar QD. When you talk about the vertices, how to write them? The vertice factors are basically depend on the momentum, or if you go to the coordinate basis, is the derivative. So we have to capture those effects also, because those are also considered as an operator. For example, I wrote down the phi square d square. This d square is like a on-shell spurion. So we have to give a status of a quantum field, but not the property of a quantum field. And d mu has a very interesting property because d mu is singlet under the internal symmetry. D mu doesn't transform under any kind of gauge symmetry or global symmetry, but it transforms as a bispinner under the space-time when you talk about the wild representations. So d mu has a transformation property only under the space-time symmetry, but these are singlet, that means they don't transform under the internal symmetry. So that is the special property about the derivative or the covariant derivative here. Okay? Okay. Yeah. As I told you, spurion is like a giving the same status to a on-shell quantum field without the property of the quantum field. I mean, it doesn't have any mode expansion and all those things. Yeah.
About the question that he answered about.
Which question?
The question about this being a total d mu instead of a del mu. The total derivative is different. But I think the type of term you will generate when you take the difference between this and the other object are total derivatives of del mu, not d. So,
Artillerism?
as in, you won't generate any other terms. As in, if you take the difference between this and the other term that you find, which you call the total derivative of the big d mu, the the big d mu is the same as the small d mu because the terms which are
Yeah, so it may actually, but the point is basically I don't need to go there. That's what I'm saying. I don't need to go there because I don't think about in terms of del mu at all. Del mu is not even in my picture. I don't have mu. So I don't have the knowledge about the mu, del mu, nothing else. I have these quantities and I have my construction of d mu at this point is just a derivative. And more importantly, why I am not worried about the d mu? Because I will use the same d mu irrespective of in which field it is acting. You understand? So it says a single d mu quantity. It's not like for every field you are injecting one d mu. It's not like that. It's a single field, spurion d mu. It is just like a tag for my derivative. Now, what is my d mu? That will be decided later on. Once we construct the operators, when we try to expand the Lagrangian to find out the Feynman vortices and so on, that time I look for what are the quantum numbers of phi and psi. That will decide that okay, what is the d mu which is acting on them. But at this point, I am not bothered about any property of the d mu apart from this is just in the while represent they are bispinner, they are singlet under the internal symmetry. I am not going to distinguish the property of the d mu at this point. I don't need that.
no, I'm saying that if this had the difference between this and the other term below had any terms that were different from total derivatives, del mu total derivative, then you would have problems dropping it because
No, I will not have because in the gauge inventory I can always drop that because that's why in the gauge invent theory d mu is my derivative.
no, but if you think of it as a norm, because you have d4x, so you have to draw with respect to that integration here.
No. Why? Because d mu contains, because it depends on how to classify your d mu. D mu contains, if I am doing the background field theory, it contains the background fields. I will drop the background field. I don't care about the background field that time. It depends on many other things. So that's why I'm saying that I don't want to go into detail about that thing, but that is certainly not necessary.
But I am saying that you are generating your
You never know. It's very simple to look into that. Have you checked about the dimension 8 operators, how they differ? So that's why I'm saying that this property I am not going to even use here because that is not a generic property for every dimension. But the more every dimension is in terms of the d mu.
So you think of this as the
Derivative. Exactly. Exactly. Because d mu is just for me, it's a derivative from the symmetry point of view. Yeah. Okay. Any other question? Yeah. Louder.
Do we worry about the form of field tensor similar way?
Which tensor?
Field tensor like
Yeah, field tensor basically, of course, because field tensor depends on the internal symmetry. Because if you have a SU3 color, you have a G mu nu, right? You have a SU2, you have a W mu nu. You have a U1, you have a B mu nu. So they are different. But what I'm saying, the D mu, you have only one in your theory when you construct this thing. You don't have the D mu for every internal symmetry and something like that. There's only one. Because this is just for a spurion tag for me to understand the nature of the derivative in my theory. So that's why when I perform the IBP, I can translate the d mu which was acting on the fermion field to through IBP, that d mu acting in the same some scalar field. The same d mu. Because all the d mu are basically half comma half and same as the derivatives. Okay. Yeah.
Sir, so you mentioned something about the on-shellness of the
I didn't say on-shellness of derivative. I say I give them the status of a on-shell mean basically. Otherwise, I cannot use it as asymptotics. I have to construct the operator which are basically constitute of the asymptotic states. So I have to give them the same status as the asymptotic states. But I am saying I will not give any other fundamental property of a quantum field. That's why I am calling it a spurion. Yeah.
So here d mu phi also has like phi class. So
Which d mu?
d mu.
D mu phi for a gauge theory? Yes. Exactly.
So here you mean d mu not transform under internal symmetry, meaning you are reading that d mu as some spurion kind of thing, and just phi transform over there actually.
Exactly. Because when you perform the d mu phi, it's actually the internal symmetry charges are actually affect your phi, not d mu. Your d mu doesn't go to d mu prime.
Yeah, exactly.
Right? It has only the space-time symmetry. That's what I meant. and whatever my gauge theory is, for example SU3 color or SU2, I have only one d mu in my theory because of that. Otherwise I have to use a d mu color, d mu electric. I don't need that thing.
But for laying it in time, it's gauge you.
No, that's why I said it's a bispinner.
Okay, you have to.
It's a bispinner, half comma half, right? I'll go to that thing. That's why, it's very easy to deal with the Wiles representation actually. You can think of it like a clubbing of psi L and psi R together. Yeah. Any other question? Okay. So then let's try to understand this little bit more. Okay. So then my definition of Lagrangian is this, okay, and here if OI has a mass dimension, let's say d, then C has a mass dimension 4 minus d, because I am working 3 plus 1 dimension. Okay, now you can see that this Ci has a mass dimension negative when you go d greater than 4, right, starting from 5, right. So then if I want to write down explicitly, how do I write down dimension 4, so up to dimension 4, and then I write down, let's say Ci O5, or let me call it C5, C6, O6, and so on. And if I want to write them in terms of, as a dimensionless parameter, what I write them? I scale them by lambda, lambda square, and so on. So this basically an infinite series of local and operators. And remember, these all the operators that I am going to construct, I am working in a local Lagrangian, so all these operators are local operators. Okay, and these word local operators are very important, because when you talk about the integrating out, we first construct the effective action, as I also mentioned in the previous lecture. But effective action is not your effective field theory, because that's a non-local effective action. You have to learn how to reduce that non-local effective action in terms of a infinite series of local operators, and then those infinite set of series what you are integrating out, that will be matched against them, and once you match order by order, then you will understand what is my C5 and C6 in terms of the model parameters. But we will not go there now. So when you do the bottom up approach, we do not have any clue about this quantity, and these all coefficients have a special name. These are called the Wilson coefficients. Okay, so in a bottom up approach, these Wilson coefficients are free parameter. We don't even know what are their origin. Okay, so that's what we have to live with. Our structure would be like, okay, how to find out the O5 and O6, and it contains only the non-redundant operators. When I'm saying, and you have to be familiar with this kind of phrase, because this is what I'm going to use again and again. When I'm saying redundant, that means basically there are operators which are related to each other by the IBP and equation of motion. When I'm saying non-redundant, that means basically you have taken care of those things, and there is no operator related to each other by those two operations. Okay, so our goal is to construct the non-redundant operators. Fine. So now, what are the possible, the structures that you may encounter and this thing? For example, pure scalar case, phi to the power n, and then you have a scalar kinetic term phi 2 d2. Okay, when I'm talking about the n, then basically n is basically belong to your Zn plus. Okay, otherwise this could create a problem for me. And then fermion kinetic term, which I'm writing as a psi square d square. You have a gauge sector, you have a x square x cube x tilde x tilde, where your x is basically equivalent to your f mu nu, and you have a u cover sector where you have a psi square phi. Now you can see the different kind of structures that I'm writing at this point. I'm just thinking of the space-time symmetry, and these are the allowed structures by the space-time symmetry. So these, irrespective of what your internal symmetry is, you will always have these kind of structures. And another important part, when I write down the Lagrangian, we write down the Lagrangian in a covariant form, right? But what we should first construct is the invariant polynomial, and that's why I have introduced this kind of polynomial. So Hilbert series method that I'm going to discuss, okay, that will give you the invariant polynomials, okay, in this particular form. And not only that, what that do actually also, that also there's a way to deal with and incorporate the constraint like equation of motion and IBP in a more mathematical way. And why that is important? That means basically whatever be your theory, okay, you don't need to calculate every time the equation of motion, especially for individual fields, and you don't need to check them. Rather, just from the representation theory point of view, okay, we can incorporate something called the momentum generating function and something else, okay, and that will take care about the IBP and equation of motion. So it will offer me all the group or the symmetry invariant polynomials, okay, at defined mass dimension, and that polynomial structures are basically the non-redundant collections. And once we have that collection of this non-redundant polynomial, we will use our field theory knowledge to translate them into a covariant form. Okay, there's a two-step process to reach to the operator construction. First, non-redundant set of group invariant polynomials, and when I talk about the polynomials that you can think of, these are just like a spurion. You are not writing phi square as a phi dagger phi or something like that, or what kind of generators and all those things. They are not there. They are already taken care of there. So we will first write down the symmetry invariant non-redundant of polynomials, and then we will use our field theory knowledge to translate that each polynomial into an operator. For example, if I have a phi square d square, so I can write automatically, I will use the field theory knowledge to write down d mu phi, or if I prefer the other form, I write down the phi box phi. But importantly, Hilbert series, when give you the polynomial, it gives you also a coefficient or the number associated with the polynomial. And what that number tells you, that number will tell you how many independent operators you can construct with 2 phi and 2d. For example, just to give you a flavor of that, if you are working in a standard model and if I play this game, then I'll see that I get this kind of polynomial from this thing. But if you do not do the way I'm going to tell you, if you do manually, you will end up writing 4 different structures that you can write in invariant way with 4 phi and 2d. But out of these 4, 2 of them are related to other 2 by the IBP and equation of motion. That means 2 are redundant. So what Hilbert series give you, Hilbert series will not give you 4. It will give you 2 phi 4 d2. And as you know, in the quantum mechanics of the vector space also you have learned that the dimension of vector space is basically unique, but the choice of the basis vectors are not unique. You can always rotate them. Same game is where out of this 4 you will write down only 2. So when you translate them from polynomial form to covariant form, that is not unique, and that's not necessary also. But at least you cannot write down more than 2. You should not write down less than 2 also. So that's why the Hilbert series method is such a powerful mathematical technique. Okay? Yeah. You have a question? It's a psi squared d. Yeah. These are primary school questions. Yeah. No, that is not a Feynman kinetic term. Don't go there. It's a typo. It's a typo. Yeah. Any other question?
So they will take The discrete space symmetry is quantitative.
You mean on the lattice?
Like parity.
Discrete space-time symmetry, or you are talking about discrete symmetry? Because when you talk about the discrete space-time, that means I am putting the fields on the lattice. We are talking about discrete symmetries. Discrete symmetry is much more simpler to do, because let me tell you why. And you guys are smarter even to do that. Once you have this polynomial, because once we started the construction, it will be clear why I am talking about the continuous symmetry. But the discrete symmetry, it has a basically, you go to phi going to minus phi, let's say, right? And then you have a first you construct all the invariant polynomials. Just you don't care phi going to minus phi symmetry. And then you filter that phi going to minus phi. So you get that thing. So automatically the odd power of the phi will be removed. So you imposing the discrete symmetry is just a filtering procedure.
That is like CU discrete symmetry. But I am saying like parity.
Parity, what kind of? Just given one example.
X square.
Hmm.
Versus the term like XX square.
Yeah.
Those are different parity.
Yes. But that's what I'm saying. When the wild basis, when you do, you write down in terms of XL and XR. So you will not only, so you will generate all the operators involving them, and when you translate them, it automatically give you two independent operators. Okay, it automatically give you those independent operators actually. I mean the CP properties and all those things. Yeah, they are automatically taken care of. Unless you later, let's say I don't want this, that's a secondary filtering, but you will give exhaustive list of that, which are allowed by the internal symmetry and space-time. Because those are basically specific properties depending on what kind of symmetry. Yeah, any other question? Okay. So this is what actually the target would be, like a constructing polynomial. Now you can see all these terms. For example, this one is a dimension 6 and so on. So already you can see some of the glimpse of what kind of polynomial structures you may expect at the dimension 6 level. Okay, so, and let's see how we can proceed along that direction. Yeah.
So like here this
Hmm.
so here space. So here if I talk about this discrete symmetry. So that means so when you construct any operators using this method. So that those operators are individually parenting your C and D.
CPT invariant, yeah, because full CPT invariant. Full CPT invariant operators you will get, and also CP variating terms also you will get. For example, XX tilde you will get, right? Because I am working a Lorentz symmetry, so of course each and every operator has to be CPT invariant.
Full operator CPT.
Yes, but also on top of that, CP variating operators and all those things you will get. Right? Exactly. Based on your demand, you can filter that thing. Yeah. Any other question? No? Okay, so let's proceed about how the Hilbert series actually construct, and also what does it mean in a polynomial form. Okay, so let's say, so first is to calculate the invariant polynomial. So we'll do first mathematical task and then we'll come back to the physics later. So let's say I have a scalar field phi, which is a complex scalar field, and phi goes as e to the power I theta phi. Similarly, phi star goes as e to the power minus I theta phi star. Right? So just for the time being, I'm thinking this is just a global symmetry. So I don't need to introduce any kind of covariant derivative and so on. Okay. So then you can see that if I have this kind of polynomial phi star phi to the power n, where n belongs to your Zn plus, okay, and 0 I am not using because it doesn't give you anything. It's a constant term actually. Okay. So you can see all the terms are basically allowed by the symmetry, phi star phi whole square, phi star phi whole cube, and you can go up to any infinite order. Okay. So then, in my definition of Hilbert series, it's a basically collection of all these symmetry invariant polynomials. So I write it down as a polynomial. Okay, so it's like a forming a monomial basis kind of thing if you think, right? And then this Cn gives you, as I told you, how many terms with phi star phi you can construct at the nth order. Okay, for example, if it is a singlet, or for example, SU2 singlet, if I have a, on top of that, if I have a SU2 symmetry, and if I have a doublet, then I have only C4 to be 1 and so on, C2 to be 1. But if I have a SU2 triplet, then these numbers will vary when I talk about the delta star or the phi star phi whole square. That means I have 2 phi star, I have a 2 phi, which are each of phi and phi star both are transforming as an SU2 triplet or the adjoint, then my Cn for that particular structure would be 3, such that I have 3 independent structures. Okay, so that's how the Cn are not uniform. It depends on at which order you are constructing this polynomial. The number of independent polynomial depends on basically at which order you are computing. Okay, and this Cn will be translated later as the number of operators. Okay, do you understand the identification? If you have any question, please ask me at this point. Do you understand what the meaning of Cn? So Cn tells you how many independent operators you can construct with n number of phi star and n number of phi. Okay, and we'll see. Yes. No. Only the polynomials. Yes. Yes. Only polynomials. There is no derivative. That's why it's a global symmetry. Okay. At this point, there is no derivative.
If you form something for so this is a scalar complex field?
Yeah, if it's a scalar complex field, and if I have a SU2 global symmetry, if I let's say impose, okay, for example, then I can see whether phi is a SU2 doublet or triplet. Based on that, my C2 will be defined. In one case, C2 is 1. In triplet case, C2 will be 3 or 4. Something I don't exactly remember, but there's a different mode. Okay. Yeah. Now let's have a quick example. Let's say I have a 2 scalar field, phi 1, phi 2 real scalar field. Okay. So then at n equal to 2, I can write down phi 1 square, phi 2 square, phi 1, phi 2. Right? So what does it mean? That means basically if each of the scalar field has a mass dimension 2, then mass dimension up to mass dimension at the mass dimension 2 and the operator constitute of the scalar field, you have 3 such operators, you can write them. So order of phi square, if I say order of phi square, I have 3 such operators. Okay. At the dimension 1, I have only 2 operators, phi 1 and phi 2. Now if you go for higher dimension, those numbers will be exponentially increasing more and more. Okay. And that you can see, you already get hopefully the notion that if you go to the higher dimension, the number of operators actually increases. Okay, and that actually increases beyond control, beyond dimension 6 and 8. It goes to reach to thousands of order for the standard model effective field and so on. Okay, so that's why by hand computation is slightly non-trivial. Yes. Now I said real singlet. So what is the meaning of phi 1 dagger, phi 2? This you are talking about this one? No. Hilbert series will give you the output to you in terms of the fields that you have introduced, in terms of phi star phi.
Understand what the definition of this is, because say you have 2 fields, phi 1 and phi 2. In that case, what would this Hilbert series be? That would be in terms of phi 1 and phi 2. Yeah,
so basically Hilbert series tells you basically when you write down in the collection, let's say, okay, and then it's a, if you write down in terms of C2 at the order of phi square, you write it down in this way, okay, That means phi square mean basically is all possible collection of dimension 2 operators. So there C2 is basically 3. So that means basically you get a 3 operators at the dimension 2, okay, in terms of that.
Order notation, that is fine.
Yeah.
There you have phi star, phi 3 power n.
Yes, so basically now, for example, let's say I have a SU2 global symmetry, okay. Now I have a 2-dimensional Higgs, let's say representation is 2, I am calling it H, and representation is basically 3, let me call it delta. Okay. Then I can write down only this term, let's say C2 H dagger H whole square, let's say. I cannot write down any other term which is independent than this one. That means basically I can write down only one of terms. So C2 equal to 1.
For that case, where you have just one scalar field, all of these Cn will be 1.
All of the Cn will be 1. No, not all the Cn. For 2, n equal to 2.
So, for a single scalar field, and with the SU250 or U170, any of those symmetries, these Tn's in this Hilbert series would all be 1.
No. Because if I go to let's say 10, then I can have many other way to construct them, na?
That have that.
Yeah, you can actually insert different kind of generators of higher dimension representations. That's what I'm actually saying. Wait, now if you have a delta, you can write down delta whole square term. Then you can have a delta tau I delta whole square term. So there are different ways of constructing them.
That is just the dimension of that.
Yeah. That's the leveling of the dimension, exactly. That's the leveling of that. So that's what I'm saying, that with the n number of phi star and n number of phi, how many operators you can construct, that gives you basically Cn. Okay. So that's why I will call, if I construct these 2 operators, for me, with this representation, my C2 will be 2. For doublet, it is 1, because I can write only one operator. And these numbers exponentially increase to the higher dimension and higher representations also. Because as you can see, if I go to the representation 2 to 3, automatically I have a multiple ways to construct them. Okay. Yeah. Okay. So now, so this polynomial, if I just have a only U1 global symmetry, then of course my Cn equal to, all the Cn will be 1 if I do not have any non-abelian symmetry. So then how do I write down this thing? So I can write down them as, for example, my H is basically nothing but my 1 plus phi star phi plus phi star phi whole square and so on. This is just a series, right? Which I can write down as a 1 by 1 minus phi star phi, and then expanding them in terms of the way you do the binomial thing. And as I told you, at this point, these are just as Spurian variables. You don't really care about the field property and all those things, local, non-local, all those things doesn't even arise at this point. It's just a variable. Okay, and because the infinite series, I don't care about the convergence and all those things at this point. So this equivalently, I can write down in terms of a complex integral theta 1 minus phi e to the power I theta 1 minus phi star minus I theta. Okay.
But there is
Hmm?
so you're putting Cn equal to 1.
I am not putting, because if I have only global symmetry 1, all my Cn will be 1. My Cn's were different when I am talking about the SU2 and all those things.
But it's so when you go to higher dimension,
Hmm.
then there is separate with some scale.
No, these are just the variable even at this point. That's what I'm saying. These are just the variable. Because you will not compute the Wilson coefficient. You don't care about that. Wilson coefficient is a parameter. You will attach that at the end of the calculation by hand.
So now you just constructing
Operators only. For example, when you write down the Lagrangian, you just first write down the H dagger H, then you throw a lambda. But you do not know what is the lambda. You just by hand you will put. Right? Exactly. The same way. Okay. So I can write down this series in terms of this complex integral. And more importantly, what you can think of is introduce a unimodular complex number z as e to the power I theta such that mod z equal to 1, and then your h you can write down a very nice way of 2 pi I mod z equal to 1 dz by z 1 minus phi z 1 minus phi square z inverse. Okay, yeah, any question? Fine, you just translate that in terms of a complex integral over a unimodular complex number mod z equal to 1. Okay, and then what you can do, you can perform this expansion. Okay, so if you perform that expansion, what you'll find out as the following very interesting structure: phi z into 1 minus phi star z inverse whole inverse is equal to actually 1 plus phi star phi plus phi star phi whole square, so on. This is one structure you'll get, and then you'll get z phi plus phi phi star phi plus this structure, and then you have a 1 by z phi star plus phi star phi plus so on, and plus z square plus 1 by z square. So many such structures you will get. Okay, but now if you use the residue theorem, what will be the answer? Only this structure you will get, because already you have a z here. Okay, and these phi's are basically just a spurion, they are not function of z. So if you use the residue theorem, it will actually project out this thing. That means we are already getting a flavor that if I can construct this kind of object, okay, then this is kind of a integral which is projecting out a certain section, and that section is nothing but invariant by this symmetry. Now the question basically, is it just an accidental thing? It's not certainly accidental thing. So what we are doing, that we are translating the language of a symmetry in terms of representation and so on, and we are mapping all those symmetry information in terms of more geometric interpretation. So without saying anything, when I am just choosing that z equal to I theta, I am doing this integral and all those things, okay, it is something more, or you can wondering, okay, why suddenly z equal to e to the power I theta? Okay, so when I am talking about the U1, because this is a global symmetry U1, that's why the complex phase actually you can think of. What I am doing, I am thinking the U1 symmetries, writing the equivalent of its torus coordinates. Okay, so what we will do and try to interpret that we have this connected compact group, okay, and then I will map those connected compact group or realize them in terms of the maximal torus, okay, and those representations will be written in terms of the coordinate of those maximal torus, okay, and that will help me to calculate something called the wild characters. Okay, don't worry, we will calculate everything one by one, but let me give you the flavor what we are going to do first. Okay, and that wild character is a collection of a unimodular complex numbers. Why? Because when we talk about in terms of maximal torus, it's a collection of U1. For example, if you have a SUN, it has a rank n minus 1, so its maximal torus is basically Tn minus 1, and I can parameterize this Tn minus 1 in terms of n minus 1 copies of U1, and each U1 is basically replaced by a unimodular complex number. So what I am writing as Z is actually parameterizing a U1. So e to the power I theta, that's how you parameterize a U1, right? Similarly, I will have a n for SUN, I have a n minus 1 rank, so I will parameterize the whole group in terms of as if like a function of this n minus 1 number of independent torus coordinates, and each coordinates are like a unimodular, like z1, z2, z3, z4 and so on. Okay, so then the equivalence would be in the symmetry representation theory, we have a given group, at this part we have a interpretation of maximal torus, I have a representations I'll have the character. So let me write that down. So now, so more symmetry or representation theory thing is more, I would call, geometric understanding of symmetry. So I'll have groups. This side I have a maximum torus of that particular group, and that's why now you can recall that I can write them only for the connected compact group. In question? Yeah.
So there is a you are picking up more in the same captures every possible operators.
For this particular case, yes.
So how will we show that whatever pool we are picking up?
No, I'll come to that. So, so that because eventually whenever you go for even non-abelian groups, in the maximal torus representation, you are actually dealing with a multiple copies of abelian. So eventually what you are doing for one particular abelian group, that you will repeat n times. So here you are picking the simple pole. They will also pick the n-1 number of simple pole because they are independent coordinate. That is the important aspect here. So that's why this is a simple example but exhaustive in a sense. This is exactly what we are going to do for nth times. Because what is your, here you are doing for U1, for SUN you will deal with n-1 number of such Z, and because these Z's they don't talk to each other because they are independent coordinates. So I always look for simple pole in terms of n-1 coordinate. Now you can see if you have a simple one term can be a simple pole correspond to n-2 coordinate, but not for the other one. That term will vanish. So so when you translate the language of the invariance from the representation theory to this language, we'll look for those terms which gives me the simple pole in terms of all the coordinates. Those are the invariant terms. Okay, yeah. So I have this side groups, I have a maximal torus. This side I have a representation, and this side I have a character. So more importantly, they are basically the wild characters. And these mapping I can do for connected compact group, and that's why we will restrict ourselves for this particular construction to the connected compact group internal symmetries. And for example, we can do this for SUN, SO2n, SO2n plus 1 and symplectic group, and of course U1. So we can write down the wild character for this connected, and when I'm saying connected, it need not to be simply connected, it can be multiply connected also. So that's why I don't bother about that thing. Yeah. So these are the possible group structures. If my internal symmetry falls in this domain, I can perform this kind of construction. For example, and if it is not falling there, I look for whether I can reduce those symmetry or realize those symmetry in terms of them or not. For example, the space-time symmetry doesn't fall in this category, and that is the reason that in 3+1 dimension I go to SU2L cross SU2R basis, and then I can use this information there, but there will be something more than that thing. So now, what is so specialty about these wild characters? They have very important property of the orthonormality. What is that? That is basically d mu chi L of some representations and chi R of some other representations is basically give me the delta LR. What is the d mu? D mu is called the hard measure. So this d mu is called the hard measure, and this is also function of torus coordinates. So all this we will learn how to calculate this thing. So that means now if I map to that thing, we will see that this is nothing but the hard measure for the E1. dz by z is nothing but the hard measure of the E1, and this is, and for the, we'll see that z and z inverse are nothing but the character of the E1. Yeah. Huh? Yeah, R is just to tag representations. No, small l, small r is a tag. That for L equal to R, this R, capital R equal to capital R prime, or they are R cross R. So basically, it tells you that for L equal to R, only R cross R prime contains a singlet. That's what it means. Okay. Now, let me translate in terms of a representations what is going on in the back of the envelope. Yes.
So, U1 cross U1 essence of the subgroup of X.
Yeah, it's a maximal subgroup. Yeah.
So, when you're constructing representation, so why are you using maximal subgroup? Like the complementary was important, will not add the complementary.
Yeah. From the represent theory point of view, this is enough to capture all my invariants. Because I just look for the diagonal subgroup, right? So because these characters are nothing but the trace of the irreducible representations, right? So, and there's a unique way of understanding from representation to the character. So I'm not going to miss out any information of that. Because everything you are constructing in terms of irreducible representation. If you may not able to write down some irreducible representation, but you don't care because we are interested in the irreducible representations. When you assign the quantum fields, they are basically the irreducible representations. Yeah. Yeah. Exactly. Yeah. Yeah.
So if I start to say SU2, so the DU would be the hard measure of
SU2, yeah.
And then chi L and chi R. So say if you look at J is equal to half.
Hmm.
So J is equal to half, so A is equal to half, Y is equal to half, then is equal to 18 half.
Yeah.
It's not, so it's like a
Yeah, I'm going to discuss that thing. Yeah. Okay. So now let me discuss this property in terms of the representation theory such that it will be much easy to understand. Let's try to recall a simple example with the SU2. So SU2, what are the allowed representation? 2, 3, 4, 5 and so on. These are all my allowed representations, right? So now we know 2 cross 2 equal to 3 plus 1, 3 cross 3 is 5 plus 3 plus 1 and so on, right? So that, what does it mean? That, so this is basically the singlet I am talking about, and automatically if you calculate, let's say 3 cross 2 is basically 2 plus 4, so there is no singlet. So now what does it mean? That means basically when I talk about the representations, if I take a SE2 doublet and another doublet, and if I take a tensor product, I can create a SE2 singlet. And at the end of the day, when you talk about the invariant polynomial, that is our target to construct all possible singlet structure to begin. Now, if I translate this first line in terms of that, what does it mean? That means if I write down the hard measure for SU2, okay, and then if I write down the chi of 2 times chi of 2, I'll get 1. So that because 2 cross 2 contains a singlet, so this is always guaranteed actually. So that means when we initially, before knowing this Hilbert series, what we used to do? We just take a tensor product, Young diagram, Young tableau technique, okay, to singlet. We don't need to do that thing repeatedly again and again. Just automatically, if I calculate the character and I perform this thing, I know that if this gives you this, this will give you this line. And similarly, if you replace by this, if you calculate, what you will find out that there is not a single term in the expansion of the character which gives you a simple pole in Z That means the whole right hand side, this will be a function of something such that this integral is 0. So this will be 0. If I have a 3 cross 3 contains 1, so then again I get at least one term which basically contains a simple pole in that complex coordinate. That means I'll get a non-zero value which is 1. And why I'm calling 1? Because all these characters are basically normalized. That's why I'm calling it 1. Otherwise you can add a weight factor and that will be suitably captured by the Hermiter and so on. Okay, so that's how these kind of tensor product are actually important. Now when you write down an operator which contains this is 6 fields, you can see that how difficult it is to by hand contracting them and all those possible. But instead of doing that, what you are doing? You are just writing the all possible characters for each such 6 fields. Let them have a scalar multiplication because they are just the variable. There is no vector notation or the commuting, non-commuting. No, it's just a simple scalar multiplication. You perform the scalar multiplication and it will project out if 1. That means with those 6 things you can create at least singlets.
So basically, this elements you are encountering in this singlet is going to someone factors in front of the how many such signals are there.
Exactly. Because what is this? The whole thing will be clear more, but at least at this point if you see Z and Z inverse, what is this? Because as I told you, this is the Hermiter for E1. Now just give me 1 minute and then I come back to this thing. So for the E1 case, which is the simplest one, the Hermiter is dz by z, and E1 has only one variable, so there is no z2, only one z. Okay, and character of E1 charge Q. And why I am separating out the E1 discussion? Because E1 is a special compared to them, because E1 is the abelian and it doesn't have any irreducible representations. What it has only charges. Then based on the charges I have to define the character, right? So if I have an object having charge, let's say Q, its character is basically chi of Q, you can think of z to the power Q. Okay, so now coming back to this example here, this phi is a spurion and this spurion is accompanied by its character, and so here actually the charge is normalized to 1, so I am writing as a z to the power 1. Now phi star has a charge -1, that's why phi star is z inverse. So you can see this is already some polynomial or function of character. This is another function of the character. Okay, now when you expand them, what they'll do, they'll so if you don't look into this integral, what you are creating, you are actually creating all possible combination of the phi star phi, right? In terms of representation theory, what does it mean? That means basically when I am doing this, I am not only creating a singlet, but I am creating 5-plate, triplet, all the representations. So here that should be also reflected. These different functions actually correspond to different representations there. That if I have a, so basically what does it mean? That means if I have these fields and then when I take a tensor product nth times, let's say I have a 2 SE2 doublet or 1 SE2 doublet. So I can write down 2 cross 2, I can write down 2 cross 2 cross 2, I can 2 cross 2 cross 2 cross 2 infinite times, and all of them will give me all possible representations, and because SE2 and all will be SE2 representations. But your goal is to find out what are the combinations give you singlet structure. You find out, okay, SU2 cross SU2 give me one singlet. You find out 3 SU2 if you multiply, you don't get any singlet term. But again, there's a 4 SU2, you get a singlet term, right? So So basically, before performing the integral, what you have to generate? You have to generate a polynomial of all the combinations, which is equivalently creating all possible tensor products, because otherwise you may miss something. Once you generate that, being biased to whether they are singlet or not, you generate everything, and then that whole polynomial is basically being projected out in an invariant plane by the Hermezar integral. So what this Hermezar is doing is actually projecting out the full polynomial into another plane where only the invariants survive. So that's what being done by the orthonormality of the characters. Is it clear how that orthonormality theorem guarantees only the projection of that quantity actually? Okay? Yeah, up to this part, any question? Fine? Okay. No man, for SU2 everything is a pseudo-real representation. What do you mean by 3 bar?
No, I think of it as that this, so the projection, one projection would be the trace. And
For SU2,
because three is the fundamental representation.
no, 3 is the adjoint representation of SU2. You are messed up with the SU3. For SU3, 3 is the fundamental representation, and there is a conjugate representation 3 bar. Yeah, 3 dimensions for SU2, spin 1. I can have a 3 dimension for SU2 and SU3. I can have a 4 dimension for SU2 and SU4. SO3. SO3 also real representations. There is, because SU2 and SO3, yes. There is no conjugate representations, because if you look at the Young diagram, it's all basically one row. 2 is 1 box, 3 is 2 box, and so on. You get only conjugate representation when there is a vertical boxes.
For SU3, 3 will have to be crossed with 3 bar.
Yes, yes, because SU3 is not a real representation. 3 cross 3 bar, yes. Yeah, any other question? Yeah, actually I don't want to go there because it's already too much for them to project on, but I will come back to them that okay, so as he has pointed out, let me poke the point here. So here I am talking about only the invariant part, but there's a more to that. For example, you may want that, okay, your internal symmetry is global. For example, like baryon number, lepton number, some of you are familiar, and as you know, the Majorana-Neutrino mass time, if you want to write down and you are looking for lepton number symmetry invariant, you never get that operator, right? Because that is not in. So what you have to look for? You have to look for which terms violate by 2 units. That means this, you have to look beyond simple pole. Okay, so you have to look for other terms, and that's how we'll come to there, that it's not about the projecting the invariants, but also for a particular global symmetry case, okay, you can project out some non-invariant terms if you are interested in. That's also possible. But just for a piece of information, I am giving this thing, but I'll come back to later when talk about the standard model effective field theory, lepton number violation, and all those things. So how to symmetry violating terms you have to project out. That's also possible. Yeah. But yeah, up to this part, any question? Okay, it's clear that, okay, how the correspondence from the representation to the things comes, and what is the purpose of the characters. Okay, good. So now let's look into the structure again a bit. Okay, so you can think of 1 minus phi z, 1 minus phi star z inverse, and the whole inverse. So let's focus on this term again, because this is the term where we can learn whole Hilbert series aspect from this. This you can write down as if like an exponential of minus log 1 minus phi z minus log 1 minus phi star Z inverse and so on. And before you ask me the question, I am taking care of all the thing in the first Riemannian sheet and all those things. So there is no branch guide and all those issues are taken care of. So we are not, so I am restricting myself in the first Riemann surface. Okay, so all those ambiguities are not there. So I can write down in this particular form, and then I can perform an expansion of the log. What I can write down as an exponential of r equal to 1 to infinity phi z to the power r by r plus phi star z inverse to the power r this thing. Okay. So in other words, what I can do now, I can rewrite my h phi star as 1 by 2 pi I mod z equal to 1 dz by z exponential of r equal to 1 to infinity phi z to the power r by r plus phi star z inverse to the power r by r, this term. Right? It's a much more compact form. I wrote it down in this particular format. Okay. And now what I identify, that this dz by z is my hard measure, and this quantity exponential of r equal to 1 to infinity phi z to the power r plus phi star z inverse to the power r pi. This thing is called the Lethistics exponential of phi star. Okay, so it's more like some kind of partition function. Huh? No, I'm not writing that. I'm just identifying this thing. Of course, I mean 1 by 2 pi I. Otherwise, you just normalize the 1. Yeah. Okay, so this is nothing but the Lethistics exponential in this language. Okay, which is more like a partition function of the characters. So now coming back to again what you have to do actually, now you can understand. So you have a given representations. For that particular representations, you have some degree of freedom. Okay, because that is your starting point to construct a theory, and then you take first one field. Okay, and then you identify, okay, so what are the representations, or how does that transform under the space-time symmetry and the internal symmetries. You identify individually them, right? And then you write down the character of that particular field under each and individual symmetries. Okay, then you associate them with this thing. For example, if I want to write down in a more compact way, how do I write down? R equal to 1 to infinity, I write down chi of phi plus to the power r plus phi star chi of phi star to the power r by r. Right? So now you can see, this is, though I have constructed this using a U1, but this becomes a global definition. So what I have to do, I have to identify the field, its representations, I will calculate its character, and then individual character will be accompanied by its spurion. Why? Because at the end of the day, Z1, Z2, everything are integrate out. So who will take care about the footprint of the operator? The spurions. So that's why the spurions are there. Okay. So, and if the conjugate fields are there, their characters are also there. But what you can see, if you have a two field phi and phi star, you calculate them and exponentially add them. So now if you have a n number of field, you just add there in a such a way, okay, and that will define your statistics for the whole representations. So such thing you have to construct for individual symmetry groups, okay, and that will give you the full giant statistics, okay, for the whole symmetry and the whole representations you are talking about, and they will be glued with this kind of a hard measure, because say U1, so I have a only dz by z. If you have a different kind of groups, these hard measure will be replaced by those groups, and you perform the residue theorem, it will project out all the invariant polynomials. So this is how we'll play the game of Hilbert series. Yeah.
So the characters are not exponential, right? The booleans inside the characters are exponential.
Hmm?
So if it's chi of phi to the power r,
Hmm.
it should be chi within the phi should be exponential.
Matlab?
Like the character is not exponential.
No, the whole thing. Because z to the power 1, the whole thing.
Here it is simple because chi is n. But if you have say z plus 1 over z, you should not square z plus 1 over z. Take
We'll see. So let's not jump around. Let's see how to proceed that thing. Yeah. Okay, so and if you see that without looking to the hard measure, if you just expand this exponential, what you will get? You will get all possible combination of phi and phi star. Some of them are allowed by the symmetry, some of them are not allowed by the symmetry. So the job of the pathistic is to make sure that you are not missing out any kind of combination of phi and phi star being biased, whether they are allowed by the symmetry or not. And then the filtering job will be done by this kind of things. Okay, so that's what we'll learn in next class. Yeah, so I'll discuss next class some property of the pathistics. Okay, and then we'll proceed with the how to calculate the characters function. So this is for the E1 case we have done, and we'll see whether these E1 things will be generalized for the SU2 or not, and so on. That we'll see actually. Okay, any question? Okay, so then.